Okay, back to solving chemical engineering problem sets. Problem number 23 of Chapter 1. Chemical plant equipment costs rarely vary in proportion to size. In the simplest case, cost C varies with size S according to the allometric equation C equals alpha times S raised to the beta power. The size exponent beta is typically between 0 and 1. For a variety of equipment types, it is approximately 0.6. Part A. For beta in a range of 0 to 1, show that cost per unit size decreases with increasing size, economy of scale. In Part B, consider the case of a spherical storage tank. The size is commonly measured by internal volume V sub I superscript T. Show that beta equals 2/3. On what parameters or properties would you expect alpha to depend? Okay, so this problem it doesn't have any units for any of the variables. But it seems to be a more abstract thing that a person who already has some experience with equipment might be able to navigate. So, cost simplest case. Okay, so my strategy for attacking this one would be to recognize the nature of a exponential equation and how it varies when the exponent is less than 1. And so it seems like size. Now, what is the units of size? It seems to be, size is commonly measured by internal volume. So the size variable seems to be variableless or dimensionless on purpose. Which I guess it has to be the case for any exponent or logarithm. So size is probably, it could be any variable with any unit, so long as that unit is divided by a quantity, like a baseline quantity, a reference quantity that has the same units, making S dimensionless, which would make sense. Then alpha would have some units that would just cause the equation to have the correct units for C. So the S raised to the beta power, that taken as a whole has no units. Alpha would carry the units. C is the cost, so alpha would be, call it US dollars per whatever. And S would just be, a sizing factor, you could say. So S raised to the beta, approximately 0.6. So let's propose something for S and see if it makes sense. So size, let's say the size of the unit is, call it, let's see, one physical dimension. They give us internal volume. So I guess a tank internal volume could be one thing. That seems to be like a storage, like a duty kind of thing. I wonder if it works for like things like horsepower or gallons per minute of capacity, or maybe even kilowatts or megawatts of capacity. So I guess it's saying as that duty or ability to do things, as that capacity increases, the cost of the equipment would increase as well. So, say a 100 watt heater would be less expensive than a 1000 watt heater, which would be still less expensive than a 10,000 watt heater. And so for, say, a line of electric heaters, there'd be a beta variable that would roughly match the increase in cost And the increase in cost wouldn't be linear. So, okay, I think I've got my head wrapped around this problem a bit, at least enough to answer the question. So, tech max, how are we going to do this? So, show that the cost per unit size decreases with increasing size. So they're trying to say well, let's see. I guess we'd have to define or put into words what I was just saying. So the equation, let's see, it is, let's just say it's useful to define, or at least to describe the variables used in the allometric equation. And let's just say insert multiple equations. We've got C, which is going to be cost, and let's call that, put that in units of USD per, and then actually, well, yeah, we're not quite sure what we're going to do about that. Alpha, which is some dimensioned sizing factor, or it's a proportionality constant for sure. And then S is a well, let's see. What if we can just do this? Describe the whole thing. That itself is a dimensionless. A dimensionless factor. And S itself is a dimensionless size ratio, and beta itself is just some, another beta. We'll just call it a dimensionless, what do they call it? They give it something, size exponent. Let's call this a size exponent. Let's call this a size ratio, and we're going to specify that it is dimensionless, because otherwise it doesn't make sense. Dimensionless size factor. So this is just a proportionality constant, and that is what carries the dimensions. USD or whatever. Let's see. I guess we could make this equation a bit more thinkable, graspable, by making it less general and giving some units to play with. So let's just do that for now, as if with some stand-in units. Or some example units. Let's use the example of a storage tank. So for a storage tank built in the United States. Tank paid for with United States dollars. USD. Storage tank of the principal or the relevant size specification for the tank is the surface area of the tank. And let's give it a unit. Let's call it meters. Let's call that cubic meters. Okay. So cost is just going to be USD, isn't it? This is a cost factor. Cost, yeah, total cost. Yeah. So cost will it won't be a ratio of anything. It'll be USD. In this example, alpha will, of course, have cost. Yeah, that'll also just be USD. Dimensionless factor. What kind of units will that have? Dimensionless factor, I'm guessing, yeah, no units. So let's just explicitly say that. No units. Size ratio, also no units. But actually, we should put the units used in this. So let's go with cubic meter per cubic meter. Do we want to specify cubic meter? Yeah, let's do a cubic meter of the. So this will be. Yeah, so it will be effectively dimensionless, but it allows us to insert something. So the top cubic meter unit, that comes from, well, let's see. Let's want to define that. Let's define the size ratio. So in order to make the equation useful, or in order to be able to plug in example equipment, plug in different, in order to be able to adjust S for, or to adjust the equation so that it can be applied to differently sized units, or units of different sizes, units of equipment of different sizes. Is that a way to say it? Let's just see. The size ratio S is the part of the equation that varies, or that changes when differently sized equipment is considered, when equipment of different sizes are considered. Let's see. It is, let's see, in order to be used in an exponential factor, it and its exponent must be dimensionless in order for the equation to make sense, I guess. In order for the units of alpha to alpha times s raised to the beta units of the quantity oh come on, really? Okay. To behave. So that the units of dimensions of the units of alpha do not have to be adjusted for different equipment for each case, or for each equipment size. I mean, that's the whole point of this equation, is that you can use different equipment sizes and say, or you can maybe do an analysis of some, like, get costs for certain sized equipment, but then extrapolate for even larger pieces of equipment, and make a guesstimate for what the cost of those theoretically sized units will be. I wonder if it works backwards. If you can make a really tiny unit and the cost goes down according to this equation as well. That's something to consider. What a nanofactory. Okay. Size ratio, blah, blah, blah. In order for the size, therefore, I'll say it is useful to define S just say S is the part equation that therefore is define S as a ratio of a ratio of the same equipment specification for two different equipment sizes, where one equipment is a reference, equipment, and the other is the one to be considered. Or one is a reference specification used as a baseline against which other equipment sizes may be compared. And let's just maybe put that into practice here. So let's call S is equal to a ratio of a size baseline against a size which is So let's not use the same variable. Let's just do small s for now. Size baseline, some attribute, some specification like the ratio of, let's see, therefore it is useful to define S as a ratio of two equipment attributes. Let's try that. No, I think I worded it correctly. Of the same equipment specification. For example, the ratio might be examples of possible equipment attributes might include for a heater, or let's see, for an air let's see, for an evaporative cooler, this attribute might be be kilojoules per second of heat removed for a storage tank. The attribute might be the surface area or it might be the volumetric capacity. Volumetric capacity for a storage tank, that you might be, yeah, volumetric capacity of the tank. And let's say, so we got something that's heat removed, we got something that's being stored. How about something that is introducing energy into a system? What's another equipment duty? Motor. Let's see. A separator. No, we got a rate. We got a static thing. In the part B example of a storage tank, the relevant attribute is probably, or the attribute relevant to cost is, do they give it to us? Internal volume. V sub I the total volume within the tank. So I guess that kind of makes this part redundant, so let's try to come up with another example. Let's see. Kilojoules of heat removed. Just what's a unit process, like a piece of equipment that might have a relevant size attribute that could be scaled up or scaled down? Let's not even worry about it. Okay. I wonder if they are given a hint with that I. What does the I mean in this variable? I think it was used earlier in the chapter to describe total volume of something. I'd like to use it as an indice for something else. It has different equipment examples. And I'm just wondering if it's possible to like not cause confusion when someone does this problem. Okay, 1.5 temperature, 1.2 dimension units. No. Okay, so specific volume is total volume divided by some mass. Okay, so I guess I'm free to use that indice, or that index. Okay, so this will be some reference volume, and this will be some variable. Where, and then let's just go ahead and define this. Definition for S, or V of T. Let's do the one that's already given. V of T sub I. That is a what did we call this earlier? Reference attribute for this example, which is volume. And then V raised of T is total volume, and it is reference value let's go ahead and give it units. Okay. So this definition for S will make sure that S is always dimensionless, because it is a size ratio. And we're not told it's a size ratio. We're just told that it's size. But to make this equation like sensible, that's how I think it should be used. Okay, and first part is just kind of easy. If beta is equal to 0 to 1, show that the cost per unit size decreases with increasing size. Okay, so to get S, cost per unit size, so it's in units of dollars. Cost is in dollars, and we want to introduce dollars per cubic meter as a concept. So to do that, we need to get units out of the right side of the equation into the left. And so doing the size ratio allows us to do that. So let's rewrite this equation with a new definition for S. And yeah, let's do that. So using equation, and then let's give this a label here. Meta shift exclamation mark. And let's call this problem, we're in 23, right? Yeah, problem 23 S. Yeah, problem 23 S, just simply S. Using the equation meta shift question mark problem 23S. The provided equation for C may be rewritten as, and then let's go ahead and do it. Did we use we did not. Okay, so let's just go ahead and copy that. And then substitute in S a ratio of what we were talking about. So let's do this. Don't copy that. Select that. Okay. Give it a number. And then we're going to go ahead and define the new units. Alpha it now has units. Well, it always had units. Yeah, so let's go ahead and just put that in. Alpha let's just say variables are defined as above. Let's try and attempt to solve for C divided by V sub I of T. Like, get that reference volume out. The idea being, like, this reference volume is like, okay, the smallest or some typical equipment size. So in this example, a storage tank, a typical standard storage tank, whose cost is known or something, against which all other storage tanks are compared. I guess I should say that. V sub I T is the volume, total volume of a typical storage tank whose cost is known, against which other storage tanks are compared. This may be as simple as specifying V sub I of raised to superscript T equals 1 meter cubed. to simplify calculation. However it is defined will affect beta. Note that beta changes, or the beta depends upon how is defined. But if we're not going to, we don't have any data or betas to work with, so we'll just go ahead and work with this definition. Okay, defined variables are defined as above. Part A asks for a cost per unit size. This can be interpreted as solving equation. Let's go ahead and put this one, problem 23, C. CV solving equation 20 CV for C over V sub I sub superscript T. And let's do that. Let's go ahead and just solve for that. Let's see what it gives us. Let's just start with the whole equation. Move C over. Let's see here. How will we do that? First, we've got to break a exponent, and that'll need a logarithm to do that. So let's take the logarithm of it, if we can. Yeah, so let's just go ahead and go for a logarithm. Logarithm, does that even work? Logarithm of C. Do we need the parenthesis? Equals logarithm of that. And is there a... Yeah, that's fine. Logarithm of alpha plus logarithm of that, which can be further simplified with that beta coming down. Let's see if we can break this up here. I think that's still the same. And let's break that up even further. natural log of something minus the natural log of something else. That first something will be this quantity. Next natural log will be this other quantity. Dun, dun. Okay. And that. What I'm trying to do is I'm trying to get the natural log of C and the natural log of that V sub I superscript T on the same side. So let's go ahead and break up that natural log of alpha plus beta, and then we're going to do this quantity here minus beta of this quantity here equals natural log of C. And let's go ahead and subtract, or add, I guess, beta. Well, let's see. Do you want to divide by beta somehow? Yeah, let's do that. Be the same thing, except every quantity here. No. So they can't do that. One step at a time. That plus beta times that equals that. We can then change this one so that the beta is back inside. And we, for simplicity, let's just keep the right side of this equation the same. Then this should allow us to combine natural log of C times this guy is that. Let's go ahead and combine these guys, or at least pull the beta in here, because we didn't have to pull the beta out. Like that. Yeah, there we go. We can really simplify this thing later. That equals that. And then we exponentiate again. So we should just have, well, dang it, no, that's not right. We're supposed to have, I feel like our dimensions didn't quite work out right, because we're trying to find C per something else. Am I going about this in a just wrong way? Can I just show like some snapshots of things that do work? Is it even possible to get that? Does that even make sense? Well, let's see. Let's go, just to make sure I'm okay. List of logarithmic identities. Yeah, so we're doing log of two things multiplied together is equal to the log of the first thing plus the log of the next thing. Yeah, so I think we're good. Oh. Yeah, I guess that makes sense. That's weird. X raised to the log of something. Base b of y is equal to y raised to the log b of x. Okay. Let's go back to TechMax. Yeah, so I was trying to get something that looks like, yeah, what I said before. C sub. I was trying to get this somehow. And maybe some kind of proportionality constant. But it's looking like it's kind of hard. Okay, split the logarithm into those two components. Then we take the beta out of the logarithm. We split the logarithm further. Vt minus v sub I. Okay. Then we distribute beta across these two terms. Then we add this term so that it appears on the left side. So we've got this and this on both sides, on the same side. Let's just see what we have. That equals that. I think that really helps us. I mean, I could have done that just without any of these steps. If beta were negative, then I'd have what I... If beta were -1, I'd have what I wanted. Can I do that, though? Could I say C times beta plus 1 times the same thing? Or what do I want to do? Because I want this somehow. So beta plus 1 minus 1. Then if we said, okay, that's equal to beta plus 1 times the same thing, but with beta minus 1. Does that make sense? Then we would have our factor, the one that we were looking for, which is C over V sub I T times, well, that. But that's just a number. I mean, we don't really care about that. Okay, so yeah, we could just say C of V sub I raised to the T is equal to this guy divided by this quantity. So going back all the way up here, we can get there faster by saying alpha times the ratio of V raised to the T raised to the beta times this raised to the beta then do this other weird trick because we're trying to get, we need a quantity well, let's see here. Yeah, we're trying to get this. Yeah, so we split the exponent and then we move over this factor to the other side. And then we do some shenanigans up in the exponent. -1 plus beta plus 1, which we then say, all right, well, which we then split into those two terms, which we then can rewrite like so. Which we can then do that. And we don't have to go into this land of logarithms. That's kind of a dead end. Not dead end, it's just a long route to get to where we are here. Same? Yeah, that's the same. Let's go ahead and delete these equations. Don't need them. Okay, so we got our ratio, which is what we were looking for. And it's kind of recursive, but this number is just a number. We don't really care. That's just a number. This alpha is just a number. This is the variable. That is what changes. So this is saying this is in units of, in our example, dollars per cubic meter. And so the cost per unit volume, this is our reference unit volume, is equal to this function. And alpha is just a constant. This is just a constant. This is the variable. This changes with whatever we want. This is what we would insert to say like a 10 cubic meter tank, a 1,000 cubic meter tank, a tank the size of the planet Earth cubic meters. Like that would be, that's the variable. So we are asked to show that for beta between the range of 0 and 1, that cost per unit size decreases with increasing size. Okay, so this thing decreases with increasing size. So as this gets bigger, this decreases. Does that happen? I don't think so. You'd think that number would just increase. Did I miss a negative in there somewhere? Am I missing something? Yeah, because like if beta were like 0.5, yeah, V, well, let's see. Increasing size. Decreases with increasing size. So size, they're talking about this. As that goes up, as V of t per that, as that ratio goes up, we're not changing this. This will just hold as a constant. So as the total volume to be considered goes up, the cost per unit thing goes down. Cost per unit volume. I feel like I'm missing something. Am I just not defining everything correctly? Put that original equation up here. Alpha is just a number, so as cost increase, as size increases, the cost per unit volume decreases. I thought I've shown that, or I've shown the cost per unit volume. Is that even right? Okay, so here's the cost in dollars. This is the unit volume. Just in this case, we're just going to call it 1 cubic meter. We split the exponent, or distribute the exponent to top and bottom. Makes sense. And then this is just a number. And you pull that number over to the left side. That's fine. Alpha times the volume raised to beta. And then in order to get this quantity, which is the same as this quantity, we do this. Like, for example, if you have 2 raised to the negative 1 plus 5 plus 1, that should be equal to 2 raised to the 5. If you split that up, 2 raised to the negative 1 times 2 raised to the 5 times 2 to the 1, that's equal to 1/2 times 2 times 2 5 times, and one last time. And yeah, there's 5 2's, and the 2 on the first, the half cancels out the 2 on the far right, and you're left with 2 to the 5th. Yeah, so that works. What am I missing, though? Cost per unit size. Did I solve for the wrong thing? Am I actually supposed to be finding not that, but that? I mean, that makes more sense. Like, the total cost divided by the total volume. I mean, that should definitely go down. How do I show that? Maybe I went about this all wrong. Okay, let's try this again. So we split the exponent. And we want to get V, this guy, to the left side. So let's go ahead and I feel like it'd be simpler if we just get rid of that denominator thing. There we go. And let's go ahead and get our -1 plus that plus 1. And then I guess we're just going to ignore this. Yeah. And then we'll split the exponent. Because what we're going to do is we're going to get -1 times that plus 1 times this. Oh wait, we don't need -1 just yet. We want positive. Well, okay. 1 plus that minus that. Okay, we still good? I think we're still good. And then we can say C V raised to T equals alpha times the rest of this. Did we need to do that? Is there a cleaner way to do that? I mean, visually, maybe. Because all we did was do this. Then split the top part into this quantity. Kept the bottom as this. So we don't need these steps anymore. Okay. So we got cost, total cost of the equipment divided by total volume of the equipment. That should decrease for beta is ranges from 0 to +1. So right off the bat, well, yeah, right off the bat, that tells me that if beta is between 0 and +1, this quantity here can never be positive, because in order to be positive, it has to be greater than 1, which it cannot be. So therefore, this quantity, like this exponent, is always less than 1. And if you look at a function raised to a negative exponent, even if it is a less than 1 exponent, it should decrease. Yeah. Let me see if I have a graphing function. Geometry, math, no. Debian graphical calculator. Don't want to run Debian on a graphical calculator, that's terrible. There was a cool app I saw. I can't remember if it was on this computer or another one, that allowed me to plot math functions relatively easily. Let's see if we can find it. Math. I don't think it was GNU Octave. All that is what would be nice. GeoGebra, maybe? ChemE plot. Let me try ChemE plot. I feel like geometry also would have worked. or GeoGebra. All right, let's see if I can do this. Let's go ahead and duplicate this. We'll go with, well, first let's see which one's worth doing. GeoGebra. Let's go with dot. I don't think GeoGebra is what I want. What was it? ChemE plot function create Cartesian plot. F equals x squared. Does that work? Yes, that works. Okay, so let me do ChemE plot then. ChemE plot. Let's go to the window, cancel, window capture, window ChemE plot. Okay. And that should, okay, good. Let's go ahead and remove that. Does that still leave TechMax? Yep, still does. ChemE plot. Okay, so ChemE plot. Let's kill GeoGebra. We don't need that. If we're going to do a, this is just plotting some random function, x squared. But if we had said 2 raised to the, let's see, x raised to the 1, that should be a line. X raised to the 0.6 should be that. And if we do that as a negative, -6, as x increases, or in our case size, the function decreases. So yeah, so even if it's -1, even if it's really close to 0, but if we knock off a few zeros, it'll be just apparent that it's still decreasing, just not much. Yep, so it's still decreasing. Plot range. Oh, I see what we're doing. Can I move? Yeah, I can. Cool. Can I zoom in? View, zoom in, Control 1, Control 2. Oh, I see. Give a window. 4 to 4. Yeah. 0.6. Okay, great. So the function is saying, or they're saying, okay, for beta is equal to ranging from 0 to -1, excuse me, for beta of 0 to +1 exclusive, does C over V superscript, or V, yeah, superscript T, does that quantity decrease? And we're showing here that in TechMax that this quantity, which is the total cost divided by the total volume, equals this function. And so we have our alpha is just a constant. This is just a constant. They're both positive constants. This is functionally the same as just some number, some positive constant, let's just call it k, times x raised to beta minus 1. So let's see, can we do, is there an equal sign that is proportional? What was the proportional thing? Do we have a equation for that? A little loop-de-loo thing? I remember drawing that in school, but I don't think it is here. Ah, here you are. Aroba tap tap. Okay. So what we're saying is this thing is proportional to this quantity, and x being this. Yep. X raised to, yeah, some number that is between 0 and just some negative number. Yeah. So beta can never be, it'll range between 0 and 1, but never be greater than 1. So this is a negative number. Yeah. So I think we've done it. Let's go ahead and just delete our previous work. We don't need it. We have what we need. Give some equation numbers to these. Don't. All right, and then we can come in with some explanations here. Close that. Maybe zoom out a bit so I can see some things. Okay. The quantity, then we'll go ahead and be explicit. Or let's go back down here. There we go. Let's go ahead and pull that out and put that somewhere down here as an explanation. I think we're still going to use those proportional things, but okay. This okay. Is it possible for me to get a plot in here that looks cool? Tools, presentation tool, insert mathematics, maybe? No. Table? No. Image? Plot. Oh, nice. Image, plot, curve, function, x raised to the 0.6. X being from 0 to 4. Let's see what that does. Busy. Ooh. That's kind of cool. If I hit backspace, does that allow me to edit it? insert image plot curve function x raised to the negative 0.6 or 0.6 minus 1, 0 to 4, okay. Maybe x 0 to 1 would be better. Rendering customized macro. Preferences. Edit macro? No. That's not what I want. I want to change the function. Do I have to just edit source? No. Oh, no. This looks scary. Close document. I think I'll break something if I do that. Okay, let's try it again. Let's do insert image plot curve. Let's go to 0.x raised to the 0.6 minus 1, but the range from 0 to 1. See what that does. I mean, it's still the same, I guess. Plot output. Is there any cool things we can do? Edit source, not going to work. Edit macro, no. Edit macro. Text source, okay, guess not. All right, so let's see if we can maybe make a insert image. Let's go with big figure. And let's see if we can just go into this figure, paste that, figure 1, the function, and we'll say x raised, f of x equals x raised to the 0.6 minus 1. I wonder if I can do the same thing with a number. Meta shift exclamation mark. Problem 23, figure 1. Figure. Figure, let's see if that works. Meta shift that. Problem 23, figure 1. Yeah, okay. Okay, so we've got that. The resulting equation give a label for this is this problem 23 cost per unit, cost per volume, C per V, okay. The resulting equation, and then let's see, meta shift question mark. problem 23, C per V is a function of V simplified. This function is ignoring the positive constants. The equation becomes, and then we'll go ahead and put in our let's see. No. We want the nice formatting in the center. Several equations becomes that, where C over V superscript T is proportional to that, which is ignoring the positive constants and substituting V superscript T with X and plugging in becomes that. Okay. This means that that quantity, or let's go ahead and go for the kill, because beta minus 1 ranges from, has the range, let's see, because 0 less than beta less than 1, negative 1 less than beta minus 1 less than 0, this means beta minus 1 always less than 0, or is less than 0. X plotted this means the function, this means when plotted X raised to the beta minus 1 must always be decreasing. For real positive X example plot with beta equals 0.6 is shown in figure 3. Okay, so because x to the beta minus 1 must always be decreasing for real positive x, c divided by v superscript t must decrease likewise decrease for increasing x values. In other words, the cost per unit volume of a piece of, in other words, according to the allometric equation, I guess I should put this there. Answer part A answer. In other words, the total cost per total unit volume of a piece of, in other words, according to the allometric equation, the total cost per total unit volume of a piece of equipment decreases with increasing size of the equipment. I guess I could say as shown in, yeah, well, let's go with that. Doot, doot. Okay, so we took this rather general equation. We said, okay, this size, in order to make sense, we're just going to call it a ratio, a size ratio of the equipment volume to some reference volume, and rewrote that equation as so. And then we said, all right, given that equation, we want to solve for the total cost per total unit volume, which is this quantity here. So cost per total unit volume right there. In order to get that, though, we have to break an exponent, do some algebra, and in the end, we can solve for that. It's kind of, I guess, recursive. Like, you're still part of the thing we're solving for is in the answer, but that is okay. We are just showing that, okay, as your total volume of the equipment increases, this ratio goes down. And that can be shown as just saying, okay, if V of t is, say, x, well, then x raised to some negative number, because beta minus 1 for the range we're considering, it must always be negative. It will be decreasing. And beta is from 0 to 1 because we were told that. But it looks like beta is typically between 0 and 1, so it may be that beta changes. It might be negative, in which case, getting bigger means that you'd be less efficient. But we're not considering that, so we've just kind of shown in the abstract that the economy of scale, this is kind of why it is from that allometric equation. So super simple, I guess. But hopefully this video shows the reasoning behind this solution. Okay, going back up. Solving part B. I wonder if I can do a thing here. Part B. Consider the case of a spherical storage tank. The size is commonly measured by internal volume V sub I superscript T. Show that beta is equal to 2/3. On what parameters or properties would you expect alpha to depend? Okay, so alpha question is probably separate. Beta is equal to 2/3. I'm guessing that for a storage tank, the relevant cost thing is the weight, the amount of material required. I do recall that valve cost, piping cost, in piping stuff, cost of a piece of equipment often just ends up being the weight of the piece of equipment. So the mass of a large valve is a good predictor of the total cost of the valve, even if the valve is rather complicated in how it's made. So for a storage tank, let's maybe try looking at the surface area of a tank. Because the volume, you might pay for volume or something, but when you buy a tank, if you're making a tank for a given volume, you are going to be welding steel plate. And so the cost is cost of welding, and that the welding depends on how many seams there are, and the total number of seams kind of depends on how much surface area you have. So it all boils down to surface area, I think. And I bet that's where that beta 2/3 comes from. So let's write that right as much. Regarding part B, it may be useful to consider the surface area of a storage tank when calculating the... That's kind of wishy-washy. Regarding part B, when calculating the total cost of manufacturing a storage tank. I guess it's implied that equipment cost is a function of how much it takes to make the thing, not how much a marketing department might charge based on intellectual property. I guess it's just considered, okay, these things are easy, like they're not that complicated to make. It's not a secret how to make them. Everyone knows how to make them, so therefore the cost depends not on how secret your knowledge is, but just how much it costs to weld a thing together. Okay, maybe it's blah 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 cost. The surface area of a tank of volume VT total volume can be calculated like so. And we'll go ahead and put in some equations where we see surface area can be calculated by relating an equation force using an equation relating volume or V superscript T and D diameter or radius, I guess. Tank radius, total volume, and tank radius. Using several equations. One equation may be one equation relates total volume in VT and with tank radius. Another equation relates surface area with tank radius. Spherical storage tank. The equation for an equation relating VT with R may be written as, and then we'll go ahead and put it in, VT total volume is equal to, then equation for a sphere, let's look that up. Equation for, so sphere volume radius. Let's see what that gives. And do we have anything wiki books? Okay, a sphere. There we go. 4/3 pi r cubed. 4/3 pi r cubed. All right, then an equation relating A of t with r maybe written as let's see, surface area. Let's go back to the browser. Looking books, surface area, sphere. Was it 4 pi r squared? Yeah, 4 pi r squared. Bloop. A of t is equal to 4 pi r squared. I'm sure there's a YouTube video about that. So we want to relate v superscript t with, well, what are we trying to do? We're trying to use the allometric equation, and we're trying to show that beta equals 2/3. So the allometric equation was this dude, which in this terms we can write it like so. So we need to plug in and replace this thing. How can we do that? How do you show the beta is equal to a certain number? Because you could solve for beta with a logarithm? Do we get anywhere with that? Well, let's see. Let's go ahead and pull that equation. It may be useful to solve equation blah for b or beta. Let's do that. And we have a number for that equation. Yes, we do. It is called p23 CV. Let's do this. Natural log of c equals natural log of that equals I guess we did go into logarithms in any case. Natural log of alpha. What ability? No. There. Not sure what was going on there. I'm just showing the steps in the logarithm calculation here. One at a time because I found that useful. Actually, we don't need to do this split because we're trying to get beta. Okay. What did that get us? Did that get us anything? I'm not sure it did. Because we're trying to prove beta equals 2/3. And surface area is probably involved. I guess the easiest way would be to just come up with two different solutions or a ratio. Like, we have to come up with a cost. Like, two data points. Like, if we suppose that it is a function of surface area, then the cost of a unit if we assume that cost is primarily a function of how much of a tank's of the surface area of a tank, then this may be written as, and we can just write it as C is, we'll use that nifty little thing. Where was that? Is it here? No. Isn't there somewhere? Yeah, okay. What is that? That is part of the insert binary relation. C is proportional to surface area. Cost is proportional to the surface area of a tank. This may be written as that. Okay, so how do we get the constant of proportionality? The constant of proportionality, we could do it like kind of semi-empirically, I guess. Let's see how we do this. Where K is some constant of proportionality. And surface area is a function of volume. It may be useful to solve for the surface area as a function of Vt. Let's just see what that does. Oh, that's where the 2/3 comes from. The exponent's in R. Yeah. Okay. Okay, let's try something. We could solve V sub t as a function of, like, in terms of R, or we could exponentiate, or what, take some root, the third root of this, and then square it, and then we'd be left with R squared. And we could plug that into this somehow, or substitute that somehow, or we could just straight up yeah, solve this for R squared, plug that into here, then we'd have A as a function of volume. Yeah, let's try that. Equation. So this one, V of, this is total volume of a sphere, so let's label it as such. Problem 23, Vt sphere. Vt sphere, maybe factor R 4 pi R squared and substituted into equation. This one. Problem 23, AT sphere. So go ahead and start with this equation. Three t is equal to 4 times pi times r. Probably not going to get it that absolute factor, so let's just do r squared instead. Okay, so we have r squared equals that. Okay, so we have a function A. The area can be expressed in terms of volume via this. Guess we could get fancy. Could you just dump all these things to a proportionality constant like so? Alt F. Alt F, tab, tab, tab. Yeah, 2/3. Or we could just not. Okay. So we got area as a function of total volume. Does that even make sense? I guess so. Volume goes up a lot, but it doesn't go up very quickly. Definitely not proportional. Directly, linearly proportional. Okay, makes sense. So we can substitute this A. We could give this K a number. Yeah, let's just do that. Where K1 is some constant proportionality. This is C. Yeah, let's give this a label. This is cost as a function of area. CA1. CK1A. May be plugged into equation. The equation for C as a function of a t in order to get a function of C in terms of V t. All right, so let's go ahead and put in equation 388 was this one. I'm going to go ahead and say K2. K2 equals K1. I get rid of that. No, it's okay. We can leave K1 in there. Okay. So K1 is like dollars per square meter of sheet metal. And K2 is just some function of transformation of that. It's just some function of K1 with that linear proportionality constant. But the point is that cost is proportional to the volume of a vessel raised to the 2/3 power. So we could compare that equation 395 here to the equation, the allometric equation, which was up here. Yeah, this one. So a constant times a number raised to a power. We have a constant times a number raised to a power. So yeah, just it looks super similar. So I guess we're gonna have we could probably get the allometric equation. I guess the total volume. Let's see here. Are we already working with some kind of ratio? I guess it all came. Right. So in equation 388, we kind of made a mistake here. Well, it's proportional to that, to area. And K sub 1 is some proportionality constant that takes out the area units. This has units of area. Yeah, that still has units of area. Size. Yes, I guess the reference volume is, well, I guess it's implied, but dang, I want to see if I can get this. in this specific example, this is okay. But I'd like to get that reference volume in there somehow. How can I do that? If I want the end result to be a ratio here, to make this more general, this comes from the equation for area. I guess I could put a ratio in here. Area to some reference area. Yeah, let's try that. So if we're already comparing the area to some reference area, example, oops, A by T equals 1 meter squared. So when we plug it in, yeah, but some reference volume. Do I put a reference volume in here somehow? Make the left side dimensionless, I have to make the right side dimensionless. I have to make both of these R's. Yeah, I'd have to take the dimensions out of everything. I mean, I guess it could be done, but it's kind of complicated. Is it really worth it? I mean, I guess I buy some generality, but dang, it's a lot to pay for. Because really all we're after is, okay, the size of something is raised to the 2/3. Okay, great. The ratio to some reference volume. We could just say, yeah, the ratio, the reference thing is just going to be a thing. Yeah, let's just take that for now. This whole idea of, where are we? Okay, I think that's far back enough. No attempt at making dimensionless functions is made. Okay. By observation, equation blah is proportional to the general allometric equation, equation blah. Let's go ahead and give this label. This is CK2, CK2VT. Do we have an equation number for the allometric equation? Allometric equation. Yes. Okay. C alpha SB. And yeah, the exact units don't matter so much because we're just saying it's proportional. The assuming beta equals 2/3. So part B, answer, bold. So it was not useful to solve for beta. I mean, we could probably maybe find a way to make it useful, but I'm not going to. So yeah, equation 395 is proportional to the general allometric equation, equation 377, assuming beta equals 2/3, which is all we were asked to do. Back up here. Dump. And then it says, on what parameters or properties would you expect alpha to depend? Alpha. So in this case, alpha would probably depend. Well, I mean, that's, I think, the hint to solve the problem is it's some proportional to, its cost is proportional to surface area. Depends upon this context, alpha depends upon K1 which is the proportionality constant between equipment cost and surface area of the tank. Proportional K1, which is a proportionality constant between equipment cost and surface area of the tank. In other words, alpha relates alpha encodes, or is how the physical cost of steel plate is taken into account when calculating equipment cost. This was achieved by assuming that alpha is principal cost, the principal factor in estimating the cost of a spherical pressure vessel is the principal factor in estimating the cost of a spherical tank is the cost per unit area of tank of the tank shell. Yeah. That must be welded together. I'll just leave it at that. In this context, alpha is proportional to K sub 1, a constant that relates equipment tank cost with surface area. Okay, I think that's it. Great. I think that's all of problem 23. Kind of a longer one. What are we at? An hour? 2 hours? 2.5 hours? Jeez. Well, that's what it takes, I guess, to properly document this. Delivery. Okay, well, I will upload this to the repository. Thank you for joining me, person of the future. You can go to the link on the bottom right, bits.ly/3IY_ND_BX. That will lead you to a PDF of this document, or you can try and locate it at the Git repository link in the description of this video. Thank you for joining me.